Hi everyone, welcome to lecture 23 of your circuit class. And lecture 23 is about introduction to AC. The objectives of this lecture: first, that you should be able to define period, cycle, frequency, angular frequency, peak value, and peak to peak value. And then you should be able to know how to obtain the phase relationship between two waveforms. The third, to understand the terms leading and lagging. And the last objective here is to know the general format of a sinusoidal in time domain. So first we will start with what we call the alternating current. First, the abbreviation of alternating current is AC or AC. Either one is okay, whether it is, let's say, uppercase or lowercase AC, that is alternating current. And then we should know that the alternating term indicates only that the waveform alternates between two prescribed levels in a set time sequence. So, what are the popular alternating waveforms? We have the first one, that is square waveform. And for a square waveform, it look like this. This is time t, and let's say if that is a voltage. So that is a square waveform. The second one, that is triangular. And for a triangular waveform, we have it as this. That is triangular waveform. And the third waveform, that is the sinusoidal waveform. And for sinusoidal waveform, it look like this. This is T, and if that is a voltage, that is a sinusoidal waveform. So let us in this class, we really concentrate on the sinusoidal waveform, and then we have to go for that in depth. So we can say here the sine wave. So we can say that the sine wave, the sine, or let's say cosine wave, is the only alternating waveform whose shape is unaffected by the circuit elements. And what we mean by circuit elements, these are resistance, inductance, and capacitance. What we mean by that, if I have a circuit over here, and these are the elements, if I'm gonna have as an input a sinusoidal waveform, we are gonna get over here, let's say, also a sinusoidal waveform. So the shape will not be changed. So if you are getting a sine, you may get output as a sine or a cosine. And the same thing that if you get a cosine, you may get a sine or a cosine. But in both cases that you will have sinusoidal waveform. This over here is an oscilloscope screen. So this is the screen of an oscilloscope. So if you look at the screen, we do have what we call divisions. So this here is one division. If it is at the x-axis, that is time division. If it is at the vertical axis or y-axis, that is voltage. Okay, so usually that we will have, let's say, the scale. If you look over here for our scale, we are saying the scale for the x-axis, which is the time, is 200 microsecond per division. So when we are saying 200 microsecond, that means This one over here is 200 microsecond, another 200 microsecond, another 200 microsecond, and you go on till you finish one cycle. So now, from this point over here up to this point over here, we call that a complete cycle. So from this point all the way up to here, that is one cycle. Okay, this value here, when the sinusoidal waveform reach its peak, we call it peak value. When we reach this value over here, that is the peak value in the negative, because as you know, that sinusoidal waveform, if the average of it is 0, then it is alternating between positive and negative. So this over here also peak value, which means that from this point over here up to this point over here, we call that peak to peak. This is here peak to peak. Now, the one cycle over here, that is a complete cycle. So in the time axis over here, if we go from this value, which is 0, up to here for a complete cycle, we call that period. And our period over here, since each division is 200 microsecond, that means really we have 5 divisions. As you can see, this is 1, 2, 3, 4, 5 division. So 5 divisions times 200 microsecond per division, we will have 1000 microsecond. So our period, which is T, is equal to 1000 microsecond. Regarding the voltage, which is the y-axis, if you look at that, that is showing 500 millivolts per division. So if you look at this over here in the y-axis, so that is one division. So going this way, each division is 500 millivolts. That means over here we have 2 divisions. That means it is what? 1000 millivolt per division, which is 1 volt. So this here, each division is half volt, 2 division is 1 volt. Then we can say that the peak value of this sinusoidal waveform is 1 volt. The peak to peak value is 2 volts, because I have 1 volt here and I have another volt over here. So peak to peak is 2 volts. So now let us do this definition. So the first thing, that cycle, and cycle is each complete waveform of 360 degrees. That means when I am going for the green, let's say sinusoidal waveform here, I'm gonna go from this point here. If you look at that, it's gonna go positive, go back to 0, then go negative, and go back to 0. And now at this point where the waveform gonna repeats itself. So all the time our period, it is at the time when the waveform gonna repeats itself. So this is our period here. So that is one complete cycle. The second definition here is the frequency. Frequency is the number of complete cycles that occur in 1 second and it is denoted by the letter F. So F is a frequency, and that is measured in hertz, which is Hz, hertz. So our frequency is equal to 1 over the period. This is period. And of course the period is in seconds because it is time. So that means 1 hertz is equal to 1 cycle per second. The third term is period. Period is the duration of 1 cycle. So period is equal to 1 over F. Four, we have amplitude. This is the distance from the sinusoidal average to either positive or negative. That is the amplitude. Then we do have what we call the peak value. The peak value is the distance from 0 to either positive or negative. Positive, of course, that positive max or negative max. Peak to peak value measured from positive max to negative max. These are the definition associated with a sinusoidal waveform. So I would like to point out the difference between this and this. So the amplitude, make sure that the amplitude is the distance from the sinusoidal average to either positive or negative, while the peak value is going from 0 to the positive or negative. So let us take an example here just to show you how we can so for example, if I have this example to ask for or to determine the frequency of the waveform of the shown figure here. So let's say that we do have a sinusoidal waveform and we would like to know the frequency of that waveform. So let's say that it looks like this. This is t in millisecond. This is 5, 15, 25, 35, and the value over here is 1. And this is, let's say, a current I of t. So first, to get our frequency, we know that frequency is equal 1 over t. That means we need this t. T is one whole cycle. So if I start from this point here and go with this, go back to its value, that is a complete cycle. So our t is equal to 25 minus 5, and that is 20 milliseconds. Since our period is 20 milliseconds, then we can find the frequency. Frequency is 1 over t, which is 20 times 10 to negative 3. And the answer here for that frequency is 50 hertz. 50 hertz. Of course that you can go from, for example, this point here to this point over here. That is also a complete cycle. So 35 minus 15, it will be 20 again, which is 20 milliseconds. We do have a term called angular frequency. Angular frequency, this is in radians per second, and it is related to frequency by the following formula, that omega is equal to 2 pi f. 2 pi f. This is our omega, and that is radians per second. So let us see through an example to determine the angular frequency of a sine wave having a frequency of 60 hertz. To get the solution, since we are asked about angular frequency, that is omega is equal to pi f, and that is 2 pi times 60, and that will be 377 radians per second, and this is our answer. Now we can proceed to the general form of a sine wave in time domain. For voltage, V of t is equal to Vm sine omega t plus theta v, and that is of course in volts. And for current, I of t is equal to Im sine omega t plus theta I, and that is in ampere. Where Vm, the maximum voltage, Im, the maximum current, omega, the angular frequency, theta v, we call it the voltage phase angle. Voltage phase angle. And theta I, the current phase angle. So let us take an example here. We would like that a 60 Hertz sinusoidal voltage source has a maximum voltage of 170 volts. Write the equation for the voltage in time domain. First of all, the time domain voltage expression is Vm sine omega t plus theta v. This is the general form. So now, if you look at that, I need this Vm, we need this omega, and we need this theta v. So first, our Vm, it is given, which is 170 volts. That is the maximum value. Our omega is equal to 2 pi f, and our f is given, which is 60 hertz. So 2 pi times 60, that is 377 radians per second. Now regarding excuse me. Now regarding the theta v, since theta v is not given in the problem because we do not have an expression, then we can put that as 0. Then from that, we just substitute our v of t. Vm is 170 sine 370 plus 0 degrees, which is simply 170 sine 370 volts. And that is our answer. Let us go over another example here. Given the current through a circuit element as I of t 3 times 10 to negative 3 sine 754 t plus 25 degrees, and that is in ampere. We would like to determine the frequency and the value of the current at 6 milliseconds. How we will do that? First, since that the question is asking us to find the frequency, we can say our omega is equal to pi f. The general form of a current sinusoidal waveform or a sinusoidal waveform of voltage, that will be in as Im sine omega t plus theta I, let's say, for the current. So this over here, this is our omega. So that means 754 is equal to pi f. And from that, we can find our f as 754 over 2 pi. And that will give us our frequency to be 120 hertz. So if we are asked about a frequency, then we know that the unit is hertz. If we are asked about angular frequency, then we should know that is in radians per second. So now we found our frequency. So now we are saying that over here, find the value of the current at 6 milliseconds. So please pay attention now here, how we can find, because I can insert here 2 or 6, I mean 6 milliseconds for this t, and this t here also, we will insert 6 milliseconds. But look at this. This value here is in radians per second times second, then we will end up with radians for the whole term. And this here is in degrees. And these do not match. So whether that we change the radians to degrees or change the degrees to radians and then find the sign. So in this way, we can say our omega t is equal to 754 times 6 times 10 to negative 3. That is for 6 milliseconds. And that is equal to 4.524 radians. Now convert omega t from radians to degrees. That will give us omega t is equal to 4.524 radians times 180 degrees divided by pi, and that will be 259.2 degrees. So now substitute. So we will get in this case I of 6 milliseconds is equal to 3 times 10 to negative 3 sine of 259.2 plus 25 degrees. And that is equal to 3 times 10 to negative 3 sine of 284.2 degrees, which is equal to negative 2.91 times 10 to negative 3 ampere, or simply negative 2.91 milliampere. Now we go to phase relations. That is not good either. So I'm gonna go here. This is good. So if you look at this over here is sine wave, and this over here is cosine wave. This is T, and if we have a voltage, that is V. So at this point here, we have 90 degrees. This point over here, we have 180 degrees. This point over here, 270, and this point over here is 360 degrees. So now if you look at these two waveforms where they cross at 0, so both of them cross at 0 at the x-axis here. So the difference, which is this, we call that phase shift. And for that case between sine and cosine waves, that is 90 degrees. So our phase shift is equal to 90 degrees. So based on that, we can say sine of omega t plus 90 degrees, that is equal to cosine of omega t. And cosine of omega t plus theta, that is sine of omega t plus theta plus 90 degrees. And sine of omega t plus theta, that is cosine of omega t plus theta minus 90 degrees. These are the identities here. So we can say the phase relationship between sine and cosine waves that cosine wave leads sine wave by 90 degrees. So the term leads, it is ahead. How come that the cosine is ahead? this is how we look at it. Which waveform reaches its peak first? So if you look at the cosine, it reaches its peak at 0, right? While the sine wave, it reaches it at 90 degrees. Because this here, it can be degrees, the x-axis, or it can be time in seconds. Okay, so the cosine reaches its peak before the sine, then we will say cosine wave is ahead of sine wave, which means that it leads the sine wave, and the phase shift between them is 90 degrees. That's why we said cosine wave leads sine wave by 90 degrees. Or we can say sine wave lags cosine wave by 90 degrees. So I hope that now you understand what we mean by leads and lags. So leads is ahead and lags is behind. So the following relationships are useful. Cosine, let's say alpha, is equal to sine alpha plus 90 degrees. And sine alpha is cosine alpha minus 90 degrees. And minus sine alpha is sine alpha plus or minus 180 degrees. And minus cosine alpha is sine alpha plus 270 degrees. So this is how we can convert from cosine to sine or sine to cosine. So when we have v of t is equal to negative Vm sine omega t, this is the same as if we are saying Vm negative sine omega t. So now when we want to, let's say, determine the relationship between sinusoidal waveforms, so determination of the phase relationship between two sinusoidal waveforms. The first thing that the frequency of both waveforms must be equal. The second condition, if, or we can say both waveforms must be expressed as sine or cosine. And the three, if they are they are not expressed in the same format as sine or cosine, then we need to transform one to the other. What that means, let me explain that for these 3 points. If I have V of t is equal to 100 cosine 377t plus 10 degrees, and I have I of t to be 20 cosine 377t minus 50 degrees. The first thing that to compare these two waveforms, I have to look at the following. That the voltage here is expressed in cosine, the current is expressed in cosine. So we are fine for the expressions. Now we look at the frequency. This frequency is 377. This frequency is 377. Then we can say that omega is equal to 377, right, for both, which means that they are equal. And then voltage in cosine and current in cosine. Then we can determine the phase relationship. Now, if I have V of t is equal to 100 cosine 377t plus, let's say, 10 degrees, and I of t is equal to 20 sine 377t minus 50 degrees, let's say. So now 377 and 377, they are equal. That means we are okay with the first condition. The second condition, that this is expressed in cosine and this is expressed in sine. Then we have to convert one to the other. So in this case, omega is equal to 377 for both. That means they are equal, which is good. Now voltage is in cosine and current is in sine. Then we have to go back to this relationship here, whether that you change the sine to cosine or the cosine to sine. So you can use one of these two identities over here. So if we want to change the cosine, then we have to add a 90 degrees with that sine. If we want to change the sine to cosine, then we will subtract 90 degrees. Let us go over an example here. Determine the phase relationship between the following set. I have V of t 10 sine omega t plus 30 degrees, and I of t is 4 sine omega t plus 80 degrees. So the solution here, First we look, are the frequency the same or the angular frequency the same? Yes, this is omega, this is omega, they are equal. Now we look at this, is that expressed here in sine and this is in sine? Then we can do that. So we can say, you can do this as I leads V by 80 degrees minus 30 degrees, which is 50 degrees. Or you can do this. You will say, okay, our V at 30 degrees, this is 30, and that is V, and I at 80, so this is I at 80. That is, here is 80 degrees. So the difference here between this V and this I is 80 minus 30, that is 50 degrees. So I leads V by 50 degrees. What about this example here? Suppose that you have to determine the phase relationship between the following set. We have V of t is equal 10 cosine of omega t plus 30 degrees, and I of t is equal to 4 sine omega t plus 80 degrees. This is our solution here. First, if you look at the omega here and the omega here, they are equal. So they have same frequency. That is great. However, that over here I have a cosine and over here I have a sine. So we have the choice whether to convert the cosine to sine or convert the sine to cosine. So we will have both of them to have the same, let's say, expression. So if we convert the cosine to sine, what we will get? We'll get V of t is equal to 10 cosine omega t plus 30 degrees. This is equal to 10, and now I'm going to convert the sine omega t plus 30 degrees. That was the original expression. However, that to go from cosine to sine, you have to add 90 degrees. Then you will have this as 10 sine omega t plus 120 degrees. So now we have the V of t, and our I of t is given as 4 sine omega t plus 80 degrees. So look at this. Now the V is in sine and the I is in sine. This is at 120, this is at 80, I mean. That means for sure that the V is leading. So V leads I by 120 minus 80. And that is by what? By 40 degrees. By 40 degrees. Let us go with the last example here. What about if we need to determine the phase relationship between the following set. So we have our v of t is given as 15 sine omega t plus 45 degrees, and I of t negative 3 sine omega t plus 65 degrees. So now, for our solution, we check in two things. The first one, that is the frequency. Both of them are omega, so they are equal. This is given in sine, and this is in sine. So we are in good shape. However, we have one of them with a negative sign. So we have to get rid of that negative. So we can say that our I of t, which is negative 3 sine omega t plus 65 degrees, that is equal to 3 sine omega t plus 65. And for this negative over here, I'm gonna add 180 degrees, because we can go with plus or minus 180 degrees. And then this is equal to 3 sine omega t plus 245 degrees. So if you look at that, our I at 245 and our V at 45, that means I leads V by 200 degrees. Please pay attention to the following. If I have, let's say, the V of t to be, let's say, 10 cosine omega t plus 30 degrees, and I of t is, let's say, 2 cosine omega t minus 50 degrees. So if you look over here, omega and omega are equal, and this is cosine, the same expression. So if you look at that, we can say our V leads I by 30 minus negative 50, which means by 80 degrees. Because look at this here. If I have this at 30, that is our V, and our I at negative 50, which is over here, right? That is negative 50. So the whole thing here is 80 degrees. That means the V leads the I by 50 degrees. By this, I believe that the lecture is done for today, or for this lecture, which is number 23. And this is over here is your homework. Thank you for watching.